Okay guys, this is the first video, and what I'm going to do is explain each of these. Okay, so right here we have a situation where the guy is jumping off the scale. Okay, so he starts at rest. When he's at rest, the scale reading is reading his true weight. Now, a scale reading is equal to the normal force, always. And if he's at rest on the scale, the weight equals the normal force. So at first, when he's standing on the scale, the normal force is, the scale reading is equal to his true weight. And then he crouches like that. Okay, let's say he's crouched. And as soon as he pushes against the scale, at the very beginning of his jump, pushes against the scale as he lifts off, starts to lift off, the normal force will become greater than his weight. So the scale will read more than his weight. So if I was 160 pounds standing there as I jumped off, depending on how hard I jumped off, the scale reading could go up to 200 pounds from 160. And then as he rises off the scale, the normal force will go back to zero. Zero at the point that his feet have left the scale. So normal force decreases back to your normal weight, but then continues to go to zero. So that would be, if you look at this, that would be our last choice. Okay, second problem. Force of 5 newtons, increase the speed of a box from a rate of 1 to 3 meters per second within a 5-second interval. So the box is accelerating. So let's say there's a 5 Newton force. I'm assuming there's no friction. Could be though, but I'm assuming there isn't any. So the applied force is 5 newtons. Okay, so that gives it a certain acceleration. Now, what change would most likely require additional force? Well, the normal force and the weight cancel each other out. And what's left is that the applied force is the only unbalanced force. So the net force is equal to MA, the net force being the applied force. Okay, the mass is not. Okay, so for a certain A, what can I do so that the force would have to increase, but I want the same acceleration? Okay, so this would be like, think about it. So it requires an additional force. So if you think about it, if I increase the net force and the acceleration is the same, to get the same acceleration, I would have to increase the mass. Because this is the second law of motion. For a given acceleration, the applied force, the net force, and the mass are directly proportional. So, for example, if you had a truck with an empty bed, here's a truck, then you're going from 1 to 3 meters per second within 5 seconds, a certain acceleration, and you want to go the same acceleration but with a heavy load. The heavy load in the back. Same acceleration. You'd have to apply more force. Okay? So force and net force and mass are directly proportional for a given acceleration. So that would be this guy right here, letter C. Okay, let's go number 3. Okay, Akbar is doing 50 newtons to the right. Lucia is, I don't know what she's doing. Okay, that's what I'm supposed to find. Okay, the mass of the cart is 10 kilograms. The cart accelerates toward Akbar, so the acceleration is to the left. Okay, so let's do a free body diagram. Here's Lucia's. There's applied force by Lucia, which I don't know, to the left. And here's applied force of Akbar. Now, why did I make Akbar's smaller? Because the net force is to the left. So Lucia is pushing harder than Akbar is. Okay, so the net force is equal to, in this case, the bigger force, Lucia's push, minus the smaller force, Akbar's push. So this is MA, net force is MA. I know, Lucia, Akbar's force is 50. So 10 given times 2, that's acceleration, equals Lucia's applied force minus Akbar's. So Lucia's force is equal to 20 plus 50 newtons. It comes out to be 70 newtons. Okay, next. Hot air balloon exerts a force of 1,200 newtons, lifting a load of 800 newtons. So the load weighs 800 newtons. So that's the weight pointing down. The only picture, okay, so it's either this one or that one. So the force pointing up, the lifting load, is 800 newtons. So the lifting force is 1,200 newtons. So we're looking for the weight is 800. We're looking for a bigger force, upward force. The lift force, I'll just say, the applied force is equal to the applied force, or thrust if you want, is equal to 1,200. So that only picture that matches is this one, letter C. Okay, number 5. If you're moving at constant velocity, what's your acceleration? Acceleration is 0, so your net force is 0. A net force is called an unbalanced force. So there is no unbalanced force. So can't be this, the first one. It would be letter B. The probe will continue on with constant velocity unless acted upon by an unbalanced force. Okay, the other ones don't make sense if you read them. This is called the first law of motion. An object in motion will continue moving with constant velocity unless acted upon by an outside net force or an unbalanced force. Same thing. Okay, so that's letter B. Okay, number 6. Okay, in order to lift an object that's on the floor or at rest or something, there's the object. The object has weight. In order to lift it, you have to accelerate it upwards. So you have to apply a force bigger than the weight, or else it's not going to move. So the upward pull or push on the object must be greater than the force of gravity. That's letter B. Number 7. Diagram represents force acting on block that accelerates 6 meters per second. Okay, so here's my acceleration. A equals 6. No friction, so there's no friction force going to the left. That just doesn't exist. Okay, so we can see that. What's the mass of the block? So basically all we're doing is net force equals MA. Okay, you can see that the normal force in this is gravity, this is the normal force, they cancel out. So we can see that the acceleration is to the right, 6 meters per second to the right, because 18 is bigger than 6. So the net force is equal to 18 minus 6, which is equal to 12. So 12 equals the mass unknown times 6. So the mass is 12 over 6, which would be the first choice, 2 kilograms. Okay, number 8. What is the size of the net force on this system? Okay, they've drawn all the forces in the picture except the tension in the rope, the tow rope, tow chain. But that really, those two tensions cancel out, which we'll learn in the next. The tension of the car pulling against the trailer is equal to the tension in the rope, the chain, tow chain, of the trailer pulling against the car, no matter what the car is doing. So what we have, we can smush those guys together, the car and the trailer. We can smush them as one thing, and the normal force and the weights cancel out. So we have 6,000 going this way. We got 1,000 going that way. The two tensions cancel out. The trailer, I said so that's the force. The engine on the car, I guess there's drag on the car, but they're all together as a system, so the drag is 1,000. And there's a drag on the trailer of 1,000 as well. So I don't know why I drew that 1,000 down there. Sorry. Dang it. Okay, so back to this. The net force is equal to 6,000 minus 1,000 minus 1,000. The arrows that go to the left minus the sum of the arrows that go to the right. Okay, so 6,000 minus 2,000 is 4,000. So that would be letter C. Okay, two more. Okay, number 9. Okay, so what is the net force on the ball during acceleration? Okay, the mass is that. We're looking for net force, unbalanced force. The mass is 0.1. They told me the acceleration is 30. So the net force is simply 0.1 times 30 is 3 newtons. So that would be your first choice. Okay, number 10. Here's a block sliding across the table at a constant speed. All forces shown except the friction force. So I'm assuming it's going to the right, and I'm assuming the friction is pointing to the opposite direction. So I should have said it's moving to the right. What is the size of the frictional force on the block? Well, if it's going constant speed, the vertical cancel out. Vertical forces cancel out. And if you're going constant speed, the acceleration is 0 in both the vertical and the horizontal direction. So friction has to balance out with applied force, I guess. So, but in the opposite direction. So friction has to equal 1.7 newtons, which would be letter D. Okay, that's it. Hope you have a good night.